Awesome. Thanks a lot for the invitation. I'll be speaking on behalf of the Google Weather team, and specifically I'll be talking about our focus on tropical cyclones. You can see that many people from the team, the researchers and engineers at the top, and also Elinor Cruz, our partnership manager, are here today. And we came here especially to know what you're interested in, what you'd like us to focus on in the coming months, and also kind of finding more opportunities for partnerships and collaborating together. Our team has focused a lot on medium-range weather forecasting. So specifically, we predict the Earth's surface and atmospheric weather variables up to 15 days ahead at 0.25 degrees of spatial resolution. How this looks like is we have a few surface variables. For instance, we have here east to west wind or like surface temperature, but also we have vertical weather variables, such as, for instance, temperature at 500 hectopascals, but also maybe 13 or 37 vertical levels. So we have seen a paradigm shift in weather forecasting by changing from traditional numerical weather-based prediction to AI or machine learning. And the first most obvious change has been that now performance has surpassed, at least in terms of traditional metrics like MSE or CRPS, that of numerical weather prediction. But also, we find it to be much faster. What used to take a supercomputer now takes just 1 minute or a few minutes on a single GPU. And maybe more importantly, we are seeing very, very fast research progress. What used to take a decade now takes 1 year. And also because our predictions are fast, we can generate years of kind of repredictions, reforecasts, in order to establish trust in our system. Concretely for our group, we started in 2022 with GraphCast. That was a deterministic model that predicted a better forecast than HRES at 6 hours of resolution. We then published GenCast in Nature that improved from a deterministic forecast to probabilistic forecast and was more accurate than ENS. And this year we published, we made public FGN, a probabilistic forecast that is more accurate than GenCast, increased the resolution to 1 hour, and is also substantially faster. It's also worth noting that we are kind of part of a wave of AI kind of improvements, such as those from Keisler, Fushi, Pangu Weather, Aurora, ForecastNet, AIFS, and many, many others. So concretely for FGN, which is our latest model from 2025, it's better than GenCast and more than doubles the gap with ECMWF ENS, and is also 8 times faster. I will not go into details on how it works, but it's loosely inspired by how in traditional numerical weather forecasting, we often perturb the physics or perturb the inputs and get slightly different predictions. So we do something slightly quite similar in machine learning land and ask the ensemble of predictions to be both accurate as well as well calibrated. You can see here a comparison between GenCast and FGN, and we obtained substantial improvements. Concretely, FGN is better on CRPS, which is kind of a probabilistic metric, than GenCast on 99.9% of the targets. And we observed between 12 hours and 24 hours of lead time improvements, which we think that because the forecasts are probabilistic, just by ingesting FGN into your pipelines, you can obtain a similar level of lead time improvements. But crucially, this last year has been a lot of, we have tried a lot of progress to move from research into impact. For instance, yesterday we were visiting GMA to see how they make forecasts in real time for Japan, but also we have been talking with many, many agencies, specifically for tropical cyclones, and we have talked with them and tried to understand what they care about. And similarly, we are here today in order to understand what you care about, to understand what we need to focus on next. Our focus has been to save lives and property, which I think is a goal we share with many of you. And so when we were looking in 2024, AI had not been deployed yet. And so we were talking to forecasters to try to understand why we were having a high research impact, but not real-world impact. And so when we were talking with them, they were saying, yes, AI is faster and can help with uncertainty by sampling many possible futures. However, I'm not seeing any real-time predictions. I'm only seeing scientific papers. And I need real-time predictions in order to trust you. They also said that AI was good at predicting cyclone tracks, but not necessarily good at predicting cyclone intensities. And also that we needed to predict cyclone structures, so how big the cyclone is in different directions. So we took this guidance and we solved this for 2025, and we're now having a very positive impact this 2025 season, both in the Atlantic as well as in the Pacific. Chatting with partners like the National Hurricane Center in the US or Weather News for Asia. So the 2025, we have now just started releasing experimental predictions with 1,000 member ensembles, leveraging the fact that FGN, our latest model, is very fast. We are now making predictions in real time. They're shared through partners as well as in Google Weather Lab. We now have state-of-the-art tracks as well as state-of-the-art intensities. So it's the first time that, at least based on historical reanalysis, we have seen that the intensities are very good. And indeed, we have started to predict very skillful structures as well. So how does this work? FGN essentially takes the initial conditions from the European agency and makes a 6-hour forecast, also in analysis land. So these are the variables that I was telling you before, like 2-meter temperature, 10-meter wind, or geopotential at 500 hectopascals. And we roll out this forecast autoregressively. So we would predict 12 hours, and here we will show up to 4 days, but actually our forecast goes up to 15 days. So now you see this atmospheric analysis rollout, and we now could run a tracker, and we used to do that, that basically tries to find cyclones in the analysis. However, this approach that AI, and in particular our team, but other teams as well, was using before, have had some issues. And that's why maybe multiple of you will have seen that previous AI models were struggling to predict intensity accurately. So the biggest issue is that the analysis is at 0.25 degrees of resolution, which is just too low to capture the very big intensities from tropical cyclones. And so the surface winds were underestimating the intensity, and they were also underestimating the size of the cyclone, and they were underestimating rapid intensification. So how did we solve it? Essentially, we just trained on better data, and we found a way to train both on dense analysis predictions, right? We have temperatures defined everywhere on Earth, but also on these sparse tropical cyclones. Tropical cyclones are not defined everywhere, but we have many, many, and up to 5,000 tropical cyclones since the 1980s, very well captured by the IB tracks and the International Best Tracks data set. So we trained FGN to both predict the analysis and the cyclones at the same time. So now, the neural network both predicts the next analysis as well as the next latitude and longitude position, the maximum velocity, as well as the different wind radii in different directions at 34 knots, 50 knots, and 64 knots. So now, if we look back at this diagram, we now see that the neural network itself makes learned cyclone predictions and learns to make cyclone predictions directly. And so now we see this 6 hours, 12 hours, and so on. We still have kind of a very simple tracker, but it's no longer the physics-based tracker. It's just something that kind of looks at what the neural network is predicting and stitches the predictions together. Crucially, we were talking about the fact that FGN is probabilistic. So we now not only sample one future, but we can sample multiple futures from 2, 3, or even 50, which is the traditional, maybe like IFS predicts 50 futures. But now, because our model is so fast, we can predict up to 1,000 futures. So of course, 1,000 futures is maybe too much information. So what we do is we aggregate them into these probability maps. And you can see here that we are able now to estimate probabilities as low as 1%. We can estimate probabilities here as low as 1%. And so this enables us to capture these kind of very rare but super impactful events and estimate the probability that a particular area is going to be impacted by high intensity winds. maybe more importantly, we're also showing very, very skillful predictions. For track, you can see that we get about 1 day improvement compared to the best global models, or the best, which are the ones that typically capture track best. So GenCast and ENS are the previous best AI model and the best numerical weather prediction model. And you can see that there is a substantial gap between them and FGN. The dashed line is because it's the moment where HAFS, which is the original model, stops predicting beyond 5 days. But of course, FGN and other models predict much beyond that. But maybe the biggest novelty is that now our AI model that has been running since early summer is now also very, very skillful at predicting intensities as well. So you can see GenCast was on par with ENS in terms of intensity, and regional models that have very high resolution, but maybe are a bit myopic, we're getting a very good intensity forecast, but now our newest model surpasses them both. And finally, in terms of extent or structure, we also see notable improvements. So you can see about 1 day improvement in track, 1 day improvement in intensity, 1 day improvement in extent, roughly. And as you probably all know, this is the type of improvement that it would typically need a decade of research in order to see this much improvement in lead time. So crucially, even though we see a lot of improvement, we still think that these AI models should be used in combination with other numerical weather prediction models, both for forecasters to understand the full perspective of a cyclone, but also as part of meta ensembles where predictions from different models are combined together in order to arrive at the best forecast. We do think, though, that AI is kind of has arrived, especially for tropical cyclones, and is ready to be used in combination with other tools. An example from October this year, our team saw that there were 2 cyclones coming to the Philippines in the coming days. I think we were seeing that in the next 10 days, one was coming very soon, and then there was going to be a second one that looked even more impactful. And so you could see here on the top left the track probabilities for the Philippines, and it was going to be quite likely that the Philippines were going to get hit by 2 cyclones in short time, and also Vietnam on the left as well. So that's actually when we started sprinting towards delivering the 1,000-member ensembles, and we shared them with Pagasa as well as Weather News in October. And that turned out to be quite accurate in terms of the track probability improvements, but also because our new model can also predict structure and intensity, we could share also with them the 34-knot wind speeds or wind radii, as well as the 50 knots and 64 knots. And you can see that the model was able to estimate where it was confident and not confident, and as the days progressed, we would be able to kind of further estimate the probabilities. So these are, I think, 10-day probability predictions, whereas usually you're probably used to seeing maybe 5-day predictions because the models lack skill much beyond that. So maybe to start concluding, I wanted to talk about the new opportunities with machine learning for cyclone predictions, as well as more generally for weather predictions. Maybe one topic that is a bit hard to think about because it's quite different from what traditional physics work like is that machine learning is very, very good at optimizing the metrics you care about. And that's why if you talk with our group, you will always hear what do you care about, what lead time do you care about, what variables do you care about. It's because when you give a goal to an AI model, the AI model will make it its life goal to just optimize the metrics you're telling it to be. That means that if you misspecify the goal, the AI will also misspecify how it targets it. Maybe one example that the weather community is quite accustomed to is that when we were working with deterministic-only models, the models were targeting lower squared error, but then they were blurring because we were not asking them to not blur. Now that we're making probabilistic forecasts and we're asking them to make realistic forecasts, now the AIs are also indeed generating realistic forecasts. Similarly, we were not telling them to care about cyclone intensities. Now we have found a way to train for general weather and cyclone intensities, and now the AI is good at that as well. So now a question for all of you is, what do you think we should make our AI models good at to best help your countries and save lives and property. The second one that we've started to see is these many more ensemble members, and this can be interpreted in two ways. The first one is, as you saw, the 1,000-member ensembles. We have seen in our preliminary evaluations internally that this allows us to capture probabilities like, of course, like 0.1%, but especially like this 1 to 10% probabilities very, very accurately because now the model is able to estimate them with many, many samples. But also these reforecasts that allows us to do research at pace, but also give forecasters 1 to 2 years of data, or even more, sometimes 3 to 4 years, so that they see that the model would have performed well in previous tropical cyclone seasons. The third one is that in internal evaluations, we have started to see that our models makes kind of quite different predictions from NWPs. And that means that the models are finding some new insights that the traditional models are not finding. And that makes it a good kind of candidate for meta-ensembling, so for combining predictions from NWPs with AI predictions. And that's something that's quite fruitful, and we've chatting with experts at Weather News as well as National Hurricane Center. We have seen that meta-ensembling is working quite well. But as you've probably are starting to get tired of me hearing, of me saying, we are very interested to hear your thoughts on what are the best opportunities to apply machine learning and AI for your countries and your agencies. So if you have thoughts, please contact us, and we'd love to chat more. So as a summary, AI now delivers state-of-the-art tracks intensities and structure for tropical cyclones, and this is also based on a state-of-the-art weather model. So that provides the core for medium-range weather forecasting, and also is now good at extreme weather forecasting. Crucially, we're moving from a world where AI, maybe you have heard about AI being good in the typical case, but maybe hallucinating in these extreme environments. We have seen that by training a single model that does good at general weather forecasting and at these extreme events, the model actually can generalize quite well to these extreme events like tropical cyclone tracks and intensities, and we think that this formula can be developed further. AI progress has been very fast. You have seen progress since 2022 to now 2025. We are progressing very, very fast, and our internal research suggests that this progress has not saturated, and we'll see continued progress in the coming years. So we highly encourage you to adopt AI and leverage these predictions. And also we are kind of starting to see that as we move from research to real-world impact, we have to find ways of collaborating with experts in order to get the best of both worlds, right? We need the AI expertise, but we also need the forecaster's expertise in order to understand how the AI should make the predictions to have the most impact on lives and property. And so the reason we are here is to help agencies leverage our AI cyclone models, as well as understand the next frontier of AI for kind of benefiting society and adaptation to extremes. That's it. Thanks a lot for your attention.